Okay, hello and welcome to my channel. Today we're going to be doing problem 3 set 2 from MIT OCW course 805 Quantum Physics 2. And today we're going to do the variational principle, which is something I haven't talked about in my lecture videos. Okay, so we'll start with problem A. Should write out the requirement first. Okay, so A, you're given that psi 1, which is an eigenstate, and psi is going to be equal to 0. So your wave function is orthogonal to the first, the ground state wave function for eigenstates. Okay, so you have to show that E2 is bounded by expectation value of Hamiltonian, which is the variational principle. And B, you assume you have a functional. You're also given that psi is real, and you have a functional. Okay, you're given this functional, and you're also given its property is that it is stationary at energy eigenstates. Okay, so stationary at eigenstate. All right. So here it mentioned critical points, which I don't know what it is. So sorry about that. So we're not going to be talking about the last part that we need, which is discussing the nature of critical points, because I don't know what it is. Okay, so I'm going to skip that, and here's take psi of x equal psi 2 of x plus sum n equal 1 epsilon n and psi n. Right. So this is a perturbed excited state. So epsilon are small. And now we have to evaluate our functional to order 2 to, right, like that. Confirm that all linear terms are cancelled. So, right, show that functional is stationary at psi 2, which is kind of extra. I don't know why you have to do that, because, well, it kind of is already stated there. But okay, let's ignore that and start with our A. Right, so first things first is that we have our psi is orthogonal to the ground state, meaning that okay, so with psi of x, you can express it as a superposition of eigenstates. So with what you're given here, you can say that your C1 is equal to 0. So we're only going to consider from n equal to 2 above so I'm gonna use the bracket notation for you to easily see the linear terms. So we're only going to consider from n equal to 2 and above equal to Cn psi n. Okay, now what we need is expectation value of h. So we're going to calculate this first and then put in the Hamiltonian, which now is just going to be En. Okay, so this is going to be equal to 1, first of all. I forgot to write that first. This is equal to 1. Okay, and now you can get your expectation value of the Hamiltonian, which you put everything the same, and you put En. That's the expectation value of your Hamiltonian. And by definition, as you increase the n, the next n is gonna have more energy than the last n. So by definition, E1 less than E2 less than En. Okay, so we get that with every n greater or equal to 2, En is greater or equal to E2. Nice. Now we expand or put in the sum part to get our bound. En is greater or equal to Cne2. Right, so from this is our Hamiltonian, and this is E2, since, well, this is specific. So expectation value of Hamiltonian is greater than E2. There we go. We've got that. Okay, that is our A done. Now we'll move on to B. B is the one that is kind of troublesome here. Okay, so f of psi, our functional of is the expectation value of Hamiltonian divided by our density probability distribution. Okay, and psi is psi 2 plus, okay, now this is where it gets interesting. The sum here, you might think that we're just gonna take what we got from A, but actually no, we're taking your energy eigenstate psi 2 and plus a perturbation. This you get from perturbation theory. Perturbation theory? Yeah. So if we put n equal to 2, meaning that including our 2, that would of course change our trial wave, which is psi 2. So we have to take n not equal to 2. Epsilon n psi n. So that's the reason why you have to do that, because your psi 2 is the trial wave plus a perturbation, and your perturbation cannot include the trial wave as well. Okay, so that is one thing to keep in mind. And now we break down our functional and calculate it part by part. Yeah, I'm afraid I won't have enough paper for it. Right, so this, now we have to split it into m and n, then merge it again later on. It's m Hamiltonian There you go. This is what you have right now. Down there, let's squish our Hamiltonian with this, and this. And that's how you do a distribution here. So first one plus the second one. Okay. Yeah, you're not given the epsilon is real, so you have to do that. Sorry, I forgot to. Wait, no. Let's write from here to here first. Epsilon m. Plus another term with both sum. Yeah. Okay, so here's where your Kronecker delta is going to do the work for you and force m to be equal to n. Okay, so do I have to classify that? Probably I should write something. So delta mn is going to force m to equal to n. Let me just write it briefly as we're running out of space. H. So now this part E2, this part orthogonal by orthogonality 0. Next part also 0. Last part now is just going to be n. And h bar psi n. Also, this is just going to equal to E2 plus some n epsilon. Okay, I forgot the epsilon here. N. Okay. This is En. Right, so now we have reduced everything to this. You see there are no more linear terms. Let's evaluate the denominator, which is probability distribution. Okay, so this first part is psi 2 on psi 2 plus sum is equal to 1. Yeah, it is. This part is also 1. Maybe I should write that too. It's also equal to 1. So we can ignore these and only take this part. Okay, so now go back to our functional. Okay, this is gonna equal to E2 plus some. Okay, don't cancel here, it doesn't work like that. Factor that out. There we go. Let's put it in a product term so that we can expand the series, which is this part. This is the part that we want to expand as series. Okay, don't have more space. Yeah, have some left here. Probably should use that too. Okay, so let's evaluate our series and see what it is. This is going to equal to 1 minus some plus. Okay, so this jumped by 2. So next one is just going to be epsilon to the 4th, which we don't really care about. Okay, so put this back into our functional. Should I just distribute it? Maybe do it a bit slower. 2 plus. Yeah. En. Okay. So order it, yeah, epsilon to the 4th. Don't really have to care about that. I don't know why I put it there. Okay. So now this is gonna equal. You can maybe use approximate. It's better. Use approximately. 2 minus some. Okay, now what? Oh yeah, I got confused there. Some en. Right. So this is what we have. Yeah, I'll just put it at this. Maybe you want it to be more neat. You can, well, factor out the common factor for these two. Put en minus e2. That would be more neat, but I don't have more space. So we will have to do with this for now. All right. This is our last thing. Okay, so we have to confirm that all linear terms in epsilon cancel and show that our functional is stationary at side 2. So pretty easy to see. Our last solution here doesn't have any linear term. And f is indeed stationary at side 2. Okay, and actually the last question is you have to discuss the nature of critical point. But as I said before, I don't know what a critical point is. So we're going to stop here. Okay, goodbye.